you check now, it should be equal to. All right, so we started this example last time, but I think it's worthwhile to kind of jump back into from scratch. There's a lot of things we had to account for. So the overall goal is the same. I want to break this very complicated rational function, this complicated fraction up into many smaller ones, and hopefully I'll be able to integrate that. So how did we start this? Right, so we had to factor the denominator, which I believe was x squared plus 1, x squared plus 4. How does this break down? So what are the smaller fractions that this breaks into? Or I mean, we know what the denominators are. What do the numerators look like? Okay. So why is it now this linear thing, this degree 1 thing, as opposed to just a constant? What's the difference between this situation and the ones we've dealt with before? The degrees of what?
Going from a quadratic to linear, I guess they're like derivatives of each other.
It's not, I mean, that is true, but I think that's kind of a coincidence. So the big idea here is that everything I've given you so far, we've started from this place. The degree of the numerator is smaller than the degree of the denominator. So degree 1 versus degree 2, degree 1 versus degree 2, degree 1 versus degree 2. And here, what's the degree of the numerator? And the denominator? 4. So we still have that place, but in breaking these things down, if we start from that place, then any of the fractions we break down, that we break that larger one into, are also going to be of the form where the numerator has a smaller degree than the denominator. So what's the degree of these denominators? They're both 2. So if I know, all I know is that the degree is going to be less than the numerator. I don't know how much less, so I want to account for the largest thing that I have to. In this case, that's degree 1. That's why I have these ax plus b and cx plus d. So we're good on that going forward. All right, so how do I continue? Okay, so multiply the denominator through by everything. So left-hand side, denominator gets cleared. What happens to this ax plus b? X squared plus 4 plus cx plus d times square plus 1. All right, so we have 4 unknowns. But what can we do? So what have we done in the past? Are there strategic x values we can choose to make some things easier on us?
You try to make x 0.
Okay, if I do x equals 0, then what does that give me? One equals 4b.
4b plus d.
Plus d. Yeah. So that didn't get me one of my unknowns, but it got me a simple equation. Go ahead.
We could choose an x value where it cancels out to 0 for one of them. For X two plus four. X two this one.
Okay, so what X value would you choose?
Well, you could do for X two plus four, you could choose,
Yeah, so that's kind of like mirage right there, because it seems like you should be able to choose a good X value there. You could choose an imaginary value of X. I will strongly discourage that. It gets out of hand. Do you remember what it looks like when you try to square or cube an imaginary number? Like you end up getting like 5 terms. So it can be done. I've seen it done. I don't encourage it. There's a lot of stuff that can go wrong. So we got one equation. Is there anything else I can do to help? Could what?
multiply it out so that you get like X cubes on one
Yeah.
side, X squares on one
So
side.
let's keep this. That might be helpful. But remember this thing where we actually just distribute everything, that's always available to us. So if I distribute this, I get ax cubed plus bx squared plus 4ax plus 4b plus cx cubed plus dx squared plus cx plus d. A lot of stuff. So now that we've expanded everything out, can I draw any conclusions about what's going on here?
Can you group the terms?
I can group the terms. So is there an equation I can write based on like grouping terms? All right, tell me more about that. How'd you get that a plus c equals 1?
If you factor out X cubed from A and C, you're left with X cubed times A plus C.
Good.
Uh,
So the only way these expressions on the left and right can be equal to each other is if all of the x cubes agree, if all of the x squareds agree, and so on. So because of that, a plus c equals 1. Can I do another similar thing? Can we follow that logic to write another equation? Sure. So, and now you're good. So I tried, the underlining doesn't make sense until it doesn't make a lot of sense until I start marking other things up. But basically, if I know that all the x cubes have to agree, so I have 1x cubed over here, right? Which means I have to have 1x cubed over there. Which means this thing plus this thing has to equal 1x cubed. So a plus c has to equal 1.
Can you do it for the x squared as well? So x squared b plus d.
B plus d equals what?
Negative. So negative 2.
Should be -2, right? So same exact reasoning. The number of x squareds on the left has to agree with the number of x squareds on the right. Let's keep on going. What else?
So it's now
X's. Give me an equation based on the x's.
plus C equals
One more time. Oh, you know what? The last equation we get is going to be this one, right? So I don't have access to other colors, but hopefully my different shapes are pointing at how I'm kind of grouping things up. So I have 4 equations, 4 unknowns. Can that help me figure out what any of my unknowns are? So I think some convenient things happen. I think if I subtract equation 1 and this one minus this one, I get -3a equals 0. So A equals 0. Double check me on that. Anytime I get a 0, I want to make sure that I didn't get lucky. But A is equal to 0, do we agree with that? If A is equal to 0, then what else do I get? C is equal to 1. So got 2 of my constants. Can I get any others? Well, I got 2 equations left and 2 unknowns. So I can do the same kind of subtraction. B minus 4b is negative 3b. D minus D is 0. Negative 2 minus 1 is negative 3. So B equals 1, right? Which means D is equal to negative 3. Let's double check those. And so I'll stop there. We just got a lot of information. Any questions on where any of that came from? Including, if you're not sure where these came from, ask me some questions now. Because
What subtraction?
which negative 3?
The negative 3a equals 0.
Sure, so this equation minus this one.
How do you know that it's not the other way around?
So let's do it the other way around. 4a minus a is 3a. C minus c is 0. 1 minus 1 is 0. Yeah, so it does not matter which way you go, that's a good question. So same, this one right here would be even more powerful because it's actually a non-zero number here. 4b minus b is 3b. Cancel. 1 minus negative 2 is 3.
And
So-
then you just subtract those equations that have the like terms of each other.
Yeah, so and that's, I didn't explain this, so maybe I'll ask why did I do this subtraction? So as I knew the C's would cancel. Same with these. Some of you, when you see stuff like this, probably like your instincts might take you to substitution. For example, if I solve for A here, I can put 1 minus C in for this and solve it that way. There are lots of ways to handle things like this. That's all I can say. So questions on where those equations came from, how we learned the things we did. If there are no questions, we can integrate, right? So what are we integrating? One over x squared plus 1 dx plus x minus 3 over x squared plus 4 dx. All right. Any thoughts about how to integrate any of that?
Use substitution.
Use substitution to do which one?
The first one.
What would your u be?
X. No, x squared.
If u is x squared plus 1, then dx would include a 2x, right?
So yeah. Then
So-
x plus.
There is kind of like a canned integral for 1 over x squared plus 1.
I think it's worse.
That's the arctangent of x integral. So that first one becomes arctangent of x. What about x minus 3 over x squared plus 4? Can I handle that?
Separate it out.
Why do I have to separate it?
I think the u substitution of squared plus 4, you don't end up with x times dx, right?
Right. So, right, the u substitution is going to fail for that reason. So, because, sorry, go ahead, Thea.
Would it also be an arctan?
Not as written, but we can build it up to one. So, you said you wanted to break this down? How would this, split up, whatever, I can't remember the word you
X
used.
over x squared plus 4 minus 3 is the integration of 1 over x squared plus 4.
So broke that into two smaller pieces. Can I do the integral of x over x squared plus 4? What does that become? I'm going to vote for the natural log of the absolute value of x squared minus x squared plus 4. Are we okay with that?
I think it's 1/2.
Okay, so a couple questions for you. What told you it was a natural log?
It's gonna be 1/u, which you did the u substitution.
Okay. Can you explain why it was going to be 1/u?
Because if we substitute x squared plus 4 for u and take its derivative, we're gonna end up with a derivative that's x times dx.
And that's what I wanted to make sure came out, is because we're not setting up like really in detail the substitution, but what we do have here is, here's a function in the denominator, and here is the derivative of that function, or some multiple of the derivative of that function. So what's the derivative of x squared plus 4? 2x. X is exactly half of that, right? So if you want, you could even see this as, I'll multiply the inside of the integral by 2, and I'll divide the outside of it by half, or by 2. So that is why that becomes a natural log, is because I have the derivative of some function divided by that function. Questions? All right. I'm gonna write this off my border so you can see it better. What is the what's the integral of 1/x squared plus 4? It is an arctangent, but it's going to be a little different this time, right? Should be arctangent of 2x this time. So I believe the form that's probably in the back of your book somewhere is this. The derivative of arctangent of ax, or yeah, ax is equal to 1/x squared plus a squared. Good.
Is it important for us to know the derivatives of the restrict functions?
Oh, I mean, mostly as a means to an end to get to the integrals.
Yeah.
So I mean, so if you'd rather, yeah, if you'd rather, we can think of it that way, but you know, most of our focus is going to be on integrals. So the derivative rules were important because of that inverse relationship. We have to know how to go those directions.
So is it important for us to know all the inverse functions?
So like to have them memorized?
Yeah.
I don't think so. I mean, in this setting, I was counting on one of you knowing it. For me to count on every single one of you to know it on a test, I think is much of story. So those things like that mean, so I'll tell you this, the arctangent one is very common, especially even compared to like the arc sine and arc cosine. I would encourage you to have this one kind of more or less locked away. But like even myself, the arc sine and arc cosine, I know I could develop them and kind of figure out what they are in a few minutes. I don't know what they are. I don't remember what they are right now.
Is it not a over x squared plus a squared?
A over x squared plus a squared.
I don't remember. It's just I'm multiplying by the derivative on the inside.
Let's find out. Oh yeah, I'm off. So let's prepare this. So the integral of
Or is it? I'm just trying to, is it a squared x squared plus 1 still?
I'm not even looking for the general rule right now. I'm just trying to integrate 1 over x squared plus 4. Yeah, we went the wrong way. So basically it's going to be 3/2 of arctangent x over 2. So let me replace this with the truth. So in general, we have this 1 over u squared plus 1 du is equal to arctangent of u plus c. So yeah, in skipping setting up the substitution, I made some bad assumptions or missed something. But this rule right here, the kind of basically identical to the one that I encourage you to kind of have locked away. But basically you have to, since we had that x squared plus 4, we have to take some care to put a 1 in that position. So for now, I'll say that last term is -3/2 arctangent of x over 2. The biggest thing I want to focus here on is let's recap. Do we understand how we broke this thing down into the smaller fractions that came out of it? Okay. Let's go again. So let's get in the habit of checking this. What's the degree of the denominator? Okay, the degree of the denominator is 5, right? What's the degree of the numerator? 4. So we're still in the right place. Make sure I know what I intended for myself. We're not going to do this one to completion. What I do want to show is I at least want to set up the form of the decomposition. So based on all the stuff that's going on in the denominator, how is this going to break down?
So 2, right at x and x squared plus 1.
So x is going to be a denominator.
And then x squared plus 1.
X squared plus 1 is going to be a denominator.
And then another x squared plus 1.
Another x squared plus 1. Just like that?
Yep.
Squared.
That one's got to be squared.
That's squared.
So why are those the 3 denominators that come out of this?
X takes care of the x.
Yeah, so the x that's the only like kind of thing you call simple here. Why do I have to have the x squared plus 1 and the x squared plus 1 squared? Why do I have to count for both of those?
To account for all possibility. I forget how you explained it. But
Yeah, so basically, and the bottom line is we have to account for all of the, so treat the thing I gave you as the common denominator of a bunch of unknown fractions that we don't know what they are yet. So because we don't know what they are, we have to account for all the things that could be. So what are all the factors of x times x squared plus 1 squared? They are simply the x and x squared plus 1, but also x squared plus 1 squared. I'll give you a numerical example. What is a good number here? Let's say I had 17 over 24. What are all the denominators that could make up that 24? I mean, really, the only prime numbers that go into 24 are 2 and 3, right? Is that true? But maybe there was some fractions that were 2 squared, which is 4, or 2 cubed, which is 8. So basically, we have to account for all the powers of these factors that are present. So because of that, I believe, yes, these are the 3 denominators I could have. Are we okay with these three denominators being the ones I have to talk about? Some of them might not exist, but we can't know that for sure. What will the numerators on these things be?
The first one would just be A, right?
First one simply A,
Bx plus c,
dx plus c.
and dx squared plus dx.
It's actually just dx plus e.
You don't need a square?
No, and here's why. So, so we talked about two special cases. One that I called a repeated factor, and I called another one a higher order or higher degree factor. Let's say this. So, what if we forgot to account for one of those? I want to make sure I keep track of everything. What if instead what we did is this: a over x plus something, and all then the only other one we had was x squared plus 1 squared. What's the degree of that x squared plus 1 squared? That's 4, right? So because of that, I would have to account for a third degree thing up here, right? So that'd be b times x squared plus 1. I don't know if this is gonna work out the way I want to. Yeah, let me swap this out for something a little simpler. I wish I could write. I know I did this for after class for someone yesterday, and I don't remember what I did. So let's say it's x over x minus 1, x plus 2 squared. So if we tried to set this up, what would the denominators be? A over x minus 1. But what if we left off the actually I can't remember what the question was now. So remember what the original question was. I think I got too lost.
Why is it not x squared on the dx plus c? Why
Okay.
not just the first part?
Gotcha. So let's keep setting this one up here. So let's do this. Let's just jump straight ahead to this term. What's the degree on this denominator here that I just wrote? That's a second degree, right? So I would do this: b times x plus 2 squared plus c times x plus 2 plus d, right? So I know carrying the 2 with it isn't exactly what we usually do, but it's going to make it easier for me to make the point I'm trying to make. Is that so? If the I already have too many things, don't I? So I don't need that d. So the thing in the denominator is degree 2. So now I have a degree 1 polynomial in the numerator, right? But am I allowed to split those up? If I split those up, what happens? I get b times x minus 2 over, sorry, x plus 2 over x plus 2 squared plus c over x plus 2 squared. Can I simplify that at all? So this one right here, a power of x plus 2 cancels. So yes, you can break it down that way, but you're going to end up in the same place. So because of that phenomenon there, that's why we can kind of ignore, basically leave off the higher orders in the numerator. They would have been canceled out. Anything else? Okay. All right, how do we do this? What are the degrees here?
2.
So the denominator has degree 2. What's the numerator have? Degree 6. So basically we have to do something we haven't done yet, and that's to get our function in a place where the degree of the numerator is less than the degree of the denominator. So this is going to have like a long division step to start with. Do you remember how to do that with polynomials? Okay, so I'll start it off. You see how we do. So I wanted to take x to the sixth and divide it by x squared minus 4. Does this look familiar at all yet? Does it look okay?
You have to have like all the,
So that's one thing that has to happen. I have to account for every place. Like basically I have to account for all powers of x, even if those powers are 0. So because of that, what do I have to do here? I have to account for all these. So that's how the setup starts. Where do we go from here?
by x to the fourth.
Where'd the x to the fourth come from?
Because we're trying to divide out. 6.
Right, so basically the first thing that happens is my leading term in the dividend, divide that by the leading term in the divisor. So what's x to the sixth divided by x squared? X to the fourth. What do I do with that x to the fourth? Multiply it by what? X squared, but also everything else. So plus 0x to the fifth.
You're subtracting.
Right, you subtract that. So this will be 4x to the fourth plus 0x cubed. All right, now what?
Squared,
How'd you get x squared?
we're dividing x squared.
I don't think we're dividing x to the fourth by x squared. We don't have x to the fourth, we have 4x to the fourth, right? So remember, this thing we have now, and I think I really should be bringing down 2 terms at once, because we're dividing by a squared. Now, we're not dividing x squared into x to the sixth, we're dividing into our new leading term, which is 4x to the fourth. So this will be, oh, sorry, these are basically I'm going to skip down pi powers 2. So 4x squared. What do I do with that 4x squared? Multiply by all the terms in the divisor. That becomes 16x squared plus 0x plus 0. So now what? What's my next term in my quotient here? Plus 16. So 16x squared plus 0x minus 64. All right, so what did we just do? I believe we're done with the division, but what did we learn? Okay, so we got our new integral, which is what? So yeah, I've got our quotient. So x to the fourth plus 4x squared plus 16, not divided by 64. What does this 64 really represent? Like it's what we had left, right?
Remainder.
That's the remainder.
So 64 divided by x.
Right, so basically plus 64. Basically what we did is this, we started at a place where the degree of the numerator was not smaller than the degree of the denominator. But how about now? I think now we have that, right? So basically we got our new integral. Where do we go from here with that integral?
So, first 3 terms.
I can integrate the first 3 terms. What do I do with the last one? It's a bit more complicated. So what do we have to do with that last one?
We just do it separately and then just do substitution.
Can we do substitution in the last one? I don't want to say no, but I'm not sure either one of those will work. But I do know something that will. Basically, that thing right there. What's that? No. You're missing a square root for all those other ones. But basically, what you can do with this is, does x squared minus 4 factor? Into what?
Plus 2x. Also just simplify to the square root of 8 over x minus 2.
That doesn't work. So a couple things. You can't, if you take a square root of that term, then you've altered it. Also, the square root of x squared minus 4 is not x minus 2. Because you're basically violating PEMDAS. All right, so can I find out what these a and b are?
Yeah.
Okay.
I think x 2.
So 64 equals a times x minus 2 plus b times x plus 2. If x equals 2, then what do I get? 64 equals 4b. So b equals 16. What's another good value for x? -2. So then I get 64 equals -4b, or 4a. So a equals -16. So I'm going to rewrite this integral one more time, hopefully just one more time. So this became what? 16 over x minus 2 minus 16 over x plus 2. All this stuff dx. Are these all integrals we can do?
Yes.
Cool. What is the integral of x to the 4th?
5x to the 5th.
1/5 x to the 5th. And then
4/3 x cubed.
good.
dx.
16x. Yeah, this is a natural log of what?
X minus 2.
Remember the absolute values. And finally,
That will also be a natural log.
yeah. -16 natural log x plus 2 plus c.
We've done trigonometric substitution on the 64 divided by x squared minus 4. If we did, basically taking the square root of both the top and the bottom.
Well, if you take the square root of the numerator and denominator, then you've altered the thing you're trying to find.
Equal.
So yeah, I mean,
Yeah.
they're also not like x squared minus 4 seems like it's a perfect square. It's not. All right, anything else on this one? So talk about, like, I think that's all the special cases to worry about. So if you have a repeated root or a repeated factor, if you have higher order factors, or if you have the degrees of the numerator and denominator are, the numerator is at least as big. One thing I want to point out is that, let's say I had this instead, x squared over x squared minus 4. Do you think you have to do the long division step for this? You actually do. We need to start from a place where the numerator has a smaller degree. So it cannot be the case where they have the same degree. Anything else? I think I got one more for you. maybe 2. I'm gonna skip that. Let's do this. Pretty gross, right? Is there anything we can do? What anything jump out at you? So everything we've done before has been polynomial divided by a polynomial. This is not one of those times. But if we could make it look like that, we'd be better off. Is there a way for us to make this look like a polynomial divided by a polynomial?
Substitution,
Substitution. What would you like to do a substitution with?
exponent,
Okay. So u equals what?
2x,
U equals 2x. If I know u equals 2x, then what's du? 2 dx.
yeah,
So if I do that, I don't think there's a way to account for all the u's. Or sorry, for all the e's. Also, only some of these can be substituted directly. Is there anything else we could use for u? X squared? I don't have x squareds. If u equals e to the x, what happens? What's du first of all? E to the x dx. Is this gonna work? What does this integral become if we do this? What's the numerator become? Not exactly u, but should be u squared. E to the 2x is the same as, so let me point this out. E to the x squared is what? E to the 2x. So I have u squared in the denominator or numerator. What's the denominator look like?
3.
I don't think it's u.
Oh, u squared.
U squared again.
U squared. It's 3u.
Plus 2. All right. What's the rest of this integral going to be? What happens to dx?
Dx would be du. Dx, dx.
Well, the dx itself is
I'm sorry,
so dx equals du over e to the x, right? Is that the same as du over u?
yes.
Okay. So can I simplify this one more time? What do I get?
So you get u squared plus 3 plus 2.
Okay.
du.
So it started with a thing that was not a polynomial. Now I have something to this. Where can I go from here?
You factor u, the denominator,
Into what?
u plus 1 plus 2. Decomposition.
The composition was like what?
A and B. U plus 1, u plus 2.
Okay. Is it really that simple? You don't know. I thought it was until you asked that, right? So is it actually that simple? What's that? It should be, right? So I have the numerator has a smaller degree than the denominator, so no division needed. Do I have any repeated factors? No, I have u plus 1 and u plus 2. Those are my 2 factors. And what are the degrees on those factors? They each have a degree of 1. So this is a good place to go. So now how can I figure out, or sorry, where do I go from here? If I multiply it through by the denominator, what do I get?
2 u plus 2.
Are there good values of u to choose? -2 is a good one. So that gives us -2 equals -b, which means that d is 2. What's another good value of u? -1. That gives us -1 equals a. So now what am I really integrating? I'm integrating -1 over u plus 1 du plus the integral of 2 over u plus 2 du. What are those integrals? The negative natural log of the absolute value of u plus 1.
It's the, it's 2 times the natural log, of the absolute value of u plus 2.
Awesome. Are we done? We're so close. What's the last thing we should do?
Put these back here.
So negative natural log of e to the x plus 1 plus 2 times the natural log of the absolute value of e to the x plus 2 plus c. How are we feeling? Wiped out?
Yeah,
Okay.
are you gonna make do long division?
Make you do long division or allow you to? It'll come up. Sorry, when you say am I gonna make you do it?
No, I mean for the exam.
Maybe, but here's the thing, what did I give you? Like I made that, so here's the thing, I made that power higher than it was because has it been recent that you've done long division with polynomials? I feel like it probably isn't, so. What's that?
So I forgot to do it.
Yeah, so I wanted to have a few cycles of this to. If you just do x squared divided by x squared minus 4, you go through it one time and don't really know what you have. Like, I wanted to make clear what things are you repeat when you do that process, because I know when I learned long division polynomials, I didn't touch it again until I got to Calc 2, and there were years of separation. I figured that was similar for all of you. But yeah, that took a while, right? So my canned answer to, am I gonna have to do this on a test, is you have 50 minutes for me to see if you understand a bunch of things, so I can't make you spend 15 minutes on any single one of them. It's not worth it. It's just not a good idea. So I can ask you about like big picture things. I can make sure you can do certain things, but it doesn't really benefit anybody for me to make sure you can spend 25 minutes on a single problem.
So didn't you say for the trig integrals, you will give us the trig identities?
Mm-hmm.
Yeah. Okay.
So here's what I can do if you'd like. I can post on Canvas. I can just take a screenshot of the given formulas from that test, but take that with the caveat that it might not be identical. I would bet money that it will be, but I can't promise you that. So I can do that when I have a second. Is I can post a screenshot of what that like reference formula section looks like.
Okay.
It shouldn't change, but I don't want to. I'm not the coordinator, so it might, but I don't think it will. Anything else? Okay, let's stop there. That's the end of section 6.3. We'll pick up with 6.4 next time. I will be in the MCC room 303 at 12. So I'll either see you there or I'll see you on Monday. Hope all the football teams you want to win.